Thanks everyone for joining our talk. It's probably the last talk between you and the keynote at the end of the day. Thanks for having us here. So we are from Confluent. This is my colleague Bonnie. He works on Flink SQL at Confluent. He's worked on several open source projects in the past, Flink, Kafka, Kafka Streams, and KSQLDB. And is interested in the broad area of large-scale distributed systems and stream processing. I'm Suhas. I'm a senior engineering manager. I manage the Flink SQL runtime and streaming AI initiatives at Confluent. And been working with distributed systems and machine learning for over a decade now. So what is Flink SQL? Right, it's a distributed engine for bounded and unbounded computation on data streams. You probably all are using Flink already. And Flink SQL has several layers of abstraction. The SQL layer is the highest level, and under the hood it also offers a table API, which is a programmatic API with declarative DSL capabilities from languages like Java and Python. There's also an even lower level API, data stream API, that gives you low-level stateful stream processing primitives like events and timers. At Confluent, on the Confluent Cloud, we offer the table API and SQL layers, but we don't actually want customers to shoot themselves in the foot with lower-level primitives, so we don't offer the data stream API. We give them capabilities to use those things as user-defined functions at the higher levels, like through the table API. And so this talk is all about changelogs. What is a changelog, right? It's a record of all changes made to a database, kind of like a bin log in MySQL. And usually there are three types of updates you can actually propagate through a changelog: an insert, update, or a delete. And in Flink, you represent inserts with a plus I, updates usually with the minus or plus U, and deletes with minus D. And so what does that mean, right? The default is an insert, and it's also like an append-only table, has only the insert changelog mode. And if it's an upsert table, you actually are updating the values for a key. You emit two records, an update before, so what is the value before the update and value after. Right, so you retract the previously emitted result with a minus U, and then you update it. And then there is also a retract where you just delete a key and you indicate those with minus D. And each Flink operator emits a different type of a changelog, and they have to be also compatible with each other. So maybe I can demonstrate that with a motivating example shortly. But there is also this stream table duality, right? And changelogs are related to that. For example, a changelog with just appends or inserts can be treated, can give you the notion of a table. Or in other words, a table would be represented as an append-only changelog with each row as a separate insert, right? And Flink has the streaming and batch modes with separate operators for streaming and batch. Streaming operators, many of operators support all changelogs, insert, updates, and deletes, but there are a subset of operators that only support either inserts and updates and not retract, or just inserts and not updates and retracts. And the batch operators specifically do not yet support updates or deletes, and that's work in progress we're actively working on. And in terms of changelog algebra, right, we do have some operators in Flink that let you go from retract or upserts to appends or vice versa. So if you want to go from retract or upsert to append, you need to have a materialization operator, which currently does not exist, and we are in the process of adding it to Flink in open source as well. And there's a sync upsert materializer, which actually takes you from a retract mode to an upsert. So and then there is the other way around. You have the changelog normalize mode, which bloats up the state by taking from going from upsert to retract. So basically, retract is the most general, which supports all of it. It could also have downsides like blowing up the state, because for each operator you're emitting 4 different types of markers downstream. We use calcite and Flink for query planning and optimization. A SQL query is parsed into a logical plan. The logical plan then gets optimized into a physical plan. With this motivating example, you have a source table, products. We want to run some aggregations on it and then write to a destination table, cumulative revenue table in this case. And we are using an over operator and summing by revenue and partitioning by category of the product with some range, and then there's some ordering as well. So if you want to see how this query gets broken down into a logical plan, you do see this from the source table scan is the operator that reads from the source, finally writing to the sink, and the intermediate operators that process the data. If there's a shuffle or a join, for example, there's an exchange operator, and then there's a changelog normalized there, which I just spoke about. And then the calc node usually does some kind of filtering, and then if there's some over aggregate, there's an over aggregate operator, right? So going more into the physical details, usually the upsert needs a primary key because you're actually updating a value and based on the primary key, right? And you also see the changelog modes when you describe the plan. This is what usually can be the append, upsert, or retract. And with this, I'll hand over to my colleague Bonnie.
Thanks, Suhas. So if you look at streaming data, you can classify them into insert streams or update streams in general. Inserts will have +i in Flink. Updating streams, as we talked about, can be divided into retract mode or upsert mode. Retract mode is also known as a full changelog mode, where you'll have +i, a -u, +u, and a -t. And for upsert, which requires a primary key to be configured when you create a table, it will emit +i, +u, and a -t. Here's a simple flow of data through the operators with changelog modes. The source, in the top part, you can see the source is producing inserts. It goes to the exchange, it goes to the over aggregate. Let's say in this case, it's an over aggregate without time attribute, so it can produce more than an insert. That is, it can also produce an insert, but a -u and a +u, and that flows through the system. Similarly, at the bottom path, you can see the source is producing update befores and update afters, which also flows to the system. As you can see, in general, from append mode, you can go to update mode, but once you go to update mode, you always remain in update mode. You cannot transition back. This was not possible until Flip 440, which introduced process table functions. That's something that you need to remember when you're dealing with changelog modes in Flink. Now, let's assume what happens if an upstream operator produces updates, but a downstream operator can only handle inserts. An example would be you have a source operator, you're doing some kind of group by, and then you're doing an over aggregate on it, and finally writing that to the sink. So your source produces inserts. Your group by is capable of taking an insert, but also producing update befores and update after. However, if you're using an over aggregate with time attribute, it does not support consuming anything like an update. So in that case, Flink throws an exception saying that over aggregate does not support consuming updates. Now you may be wondering what if certain operators ignore updates completely? Let's just stick to inserts. What happens in that case? I have an example here with group by to demonstrate what happens if certain operators decide to consciously ignore updates or changelog modes like insert, update before and update after. So let's take a simple example with users table, which has 3 fields, user ID, department, and a boolean to indicate whether the user is active. You insert 2 rows with 2 users, Alice and Bob. Alice belongs to the HR department, Bob belongs to the IT department. You start a streaming query, which is a continuous query. You do a group by department, and you count the number of users by department. So when you do that, you may see results like HR is 1 and IT is 1, which is the correct result. The changelog mode associated to it is +i or insert only. Now, let's say if Alice decides to switch departments, you update the query, and Alice moves from HR to IT. Now, If you only support insert, the result will be IT is 2, has 2 users, which is correct. But the previously emitted value of HR with the value 1 is incorrect now. To fix this, group by needs to retract the previously emitted result with a -u for HR and then update the new value for HR with the value as 0. Similarly, for IT also, it should retract the previous value and then emit the new value of IT, so to maintain correctness for downstream operators as well as downstream consumers. Operators can have different implementations based on changelog mode. In general, most more complex operators can have large state size. They can produce a lot of network traffic. It can lead to increased latency or use more compute. We'll go through a few operators now and see how it affects these variables. Here is the first example with overaggregate, which uses a time-based attribute. So we have a sensor readings table, and we are trying to compute the average temperature over a 5-minute window. So you have a select query here which does an average, and you have an over clause there which specifies that you want to do it over 5 windows, you want to partition by sensor ID and order by reading time. Here, when you execute this query, the state size is limited to the number of records that fit within the 5-minute window. The network traffic is also limited to insert only records because the window is collected for 5 minutes. Once the result is computed, the results are emitted as inserts only. And the computation is also limited to 5 minutes. So you can see how state size, network, and compute gets affected with this query. Flink 19059 extended over aggregate operator to support retractions with non-time attributes, specifically with non-time attributes. Here you can see you have a table in insert mode. You create the cumulative revenue table in retract mode, and you have this similar query for over aggregate. But in this case, you can see that the range is unbounded. That is, you want to look for everything and adjust the computation as new values arrive. If you look at the plan, the stream over aggregate remains the same, but it is now a non-time attribute over aggregate operator. Let's try and understand how this non-time over aggregate operator processes data. Let's say you have the queries shown on the top right. You get the first record with P01. Data is partitioned by category. So since category is electronics, all data belonging to electronics comes to the same node. And you're ordering by year and month. So the first record comes in, you add it to the state, and since it's the first record, you emit a +i, that is insert only, and you also emit the computed value for using basically calculating the cumulative revenue. The next record comes in, it's added to the state, and a +i is emitted for P02. Similarly, P05 product comes in, you do the same, and finally P06 comes in. Now let's see what happens when an out of order insert comes in. P04 comes in. The right position for P05 in the state is it's inserted in the right position in the state, but once it's inserted into the state, now we emit +i for the P04 product. But if you see all the values that are in the state after P04, that is basically P05 and P06, they are incorrect now. So we need to send retracts for those, that is -u, followed by an updated value for those. What happens if a record is deleted? It's very similar. You find the record, you delete it from the state, you send a -d for that record because that record has been deleted. And for all the values in the state after that, you send a retract for it, that is -u, and then an update after for that with the new computed value. As you can see, with non-time attributes, the state size can grow very large unless you are retracting constantly. Large state can add to increased latency because you have to probably read the entire data, deserialize it, and serialize it back when you updated the state. Data skew can also lead to uneven load access. Network traffic is also increased because for each record that comes in, you are potentially writing more than one record out. How can you deal with this? At the operator level, you can possibly configure TTL if you know your data pattern. That can help reduce the state size. Now, what happens if your sink supports upsert semantics? Now, when your sink supports upsert, what the plan does here is it creates a sink with something called a sink upsert materializer, and you can see that when you look at the plan by doing an explain, you will see there will be an upsert materializer set to true for the sink. So there are some rules associated to the sink upsert materializer. For insertions, the first record is emitted as an insert. Subsequent records are emitted as an update after. For deletions, if the state becomes empty, a delete is emitted. If deletion affects the latest record, the previous record is emitted as an update after. These rules allow downstream systems for a consistent view. We'll see this with an example. Now, let's say you have a table with the schema ID, name, age, city, and region ID. And let's say the region ID serves as the upsert key. Notice that we are not using the ID as the upsert key, but the region ID here. So the first record comes in with ID1 and region ID1. We add that to the internal state, and it is emitted as a insert because it's the first record. When the second record comes in, it belongs to the same region ID, so it's added to the state with the region ID as the key. The value, it maintains a list of all the values associated to the same region ID. So both Alice and Bob records are maintained, and it updates because an insert was already emitted for that region ID. Now it sends an update after. If you update a specific record that is already been in the state, it goes and updates that record in state, finds the right position, and also emits an update after for that. If you delete the last record from the state that you've seen, what it does is it emits the previous value in the state with an update after. So this is just an update after where you're inserting a new record. It adds to the state and emits the latest value, which is Robert in this case. And if you delete it, it will emit the new value of Alice, which is the previous value in the state. Finally, if you delete the last value in the state, that's when a -d is emitted. This, as you can see, for each key, that is the upsert key, it needs to maintain a lot of values associated to it, basically the entire historical data. So this can lead to a lot of data that you read from and write when you're processing through this sink upsert materializer operator. To avoid this sink upsert materializer, what you could do is you can define the primary key for the source and the sink and try to match them whenever possible, so that this expensive sink upsert materializer is not introduced or does not need to maintain the historical values for the upsert key. And if you're using group by or any kind of aggregation, try to make sure the primary key matches with the sink's primary key. Flip 544 is trying to introduce a new version of sink upsert materializer where they're trying to address these issues that I've mentioned with sink upsert materializer. Now, what happens if the source supports upsert mode? That is, you define that with when you create the table, the source table, you define the primary key. The changelog mode is upsert. What happens in that case? Let's see the plan here. So as you can see, a new node called as stream changelog normalize has been introduced by the planner. This node is responsible to deal with upsert mode as in the source and try to produce. And if your sink supports retract, it tries to deal with that case. Basically, it maintains state per key. Changelog, it converts an irregular stream that is like an upsert stream into a full changelog stream. That is, it is capable of producing inserts, update before, update after, and delete. It can also do duplicate detection correctly, basically by using the primary key defined in the table. Let's see this with an example. Let's say you have a simple key value pair, and let's say you introduce a key called 101 with an amount here, which is the first thing is, let's say if you're seeing the record for the first time, it will be a +i. you add that. Basically, what the changelog normalized node does is it adds that to the state and it emits the value out. A new key comes in, it adds that to the state, and then it emits a plus I for the new key. If you update the key from a previous amount to a new amount, what it does is it updates the value in the state, and it sends for the network traffic, it emits an update before with the old value and an update after with the new value. And if you delete a key by specifying the value as null, in that case, what it goes ahead and finds the key in the state, removes that, and sends a -d here. As you can see, changelog normalized node also tries to maintain a lot of state. So you may wonder why your states. This is probably one of the reasons why your state is blowing up when in your Flink application. Flink 540 introduces some changes where they try to remove the changelog normalized node whenever it's not required. One such example is if you're reading from an upsert table and writing to an upsert only table, you probably don't need the full changelog mode. That is, you don't care about retract. To summarize, you can see how changelog mode affects internal state, how it affects compute, how it affects latency and network traffic. If you know how your operators behave, what you can do is you can and you know your data pattern, you can define TTLs at the operator level to keep the state size small. You could use explain to see how your query is planned. Explain shows you what changelog mode is being used at each operator level. It can also give you hints like what are the potential states, like state heavy operators. And the last thing you could do is you could also rewrite queries that you require. Basically, you could break the queries and write it in such a way that those state intensive operators are not introduced. Questions? Yeah, and Confluent is hiring. If you have any experience with Flink or any batch systems like Flink or streaming systems, feel free to reach out to Suhas.